So let's do a few more examples here of finding the relative extrema and concavity of a function of x. And for this next example here, oops. Just once again, find the relative extrema and concavity of f of x, where f of x is going to be x to the fourth plus 4x cubed minus 15. All right. So again, let's split this problem in two parts. First part, relative extrema. Second part, the concavity of that function. All right, so part A, the relative extrema first. And again, since we have covered several examples of relative extrema, I'll be skipping some steps in between here. All right, so the first step to find the relative extremas, find the first derivative. So f prime of x. All right, so the first derivative of this function will be, let's see, derivative of x to the fourth will be 4x cubed. Derivative of 4x cubed, bring the power down, multiply the coefficients, decrease the power by 1 to give us 12x squared. And that's it, because the derivative of negative 15 is just 0. All right, so now we set this first derivative equal to 0, so 4x cubed plus 12x squared. Let's see what we can factor out here between these two terms to help us solve for x. Oh, what do these two terms have in common? 4 and 12 have a 4 in common, x cubed and x squared. Notice at a minimum, these two have two factors of x in common. So we can take out a 4 and an x squared, leaving us with on the inside leaving us on the inside with x plus 3. All right, equal to 0. And now set each factor of x, set equal to 0 and solve for x. So don't forget, since the outside here, since this 4 on the outside has an x attached to it, then this also has to be set equal to 0. So we have two equations to solve for here. 4x squared equal to 0, and then x plus 3 equal to 0. Solve for x to give us x equals 0 and negative 3. So we have two critical numbers. All right, so now it's time for that first derivative test. So again, we draw a number line, draw two critical values here first. So at negative 3 and 0 in ascending order. And again, if we were to plug in these two critical values into our first derivative, it will give us 0 each, because these were the zeros that we solved from that equation. All right, so now let's pick some test points here. Let's do negative 4. I'll do negative 1, and then positive 1. And again, we plug these into the first derivative to determine the behavior, the direction of the original function. All right, so if we plug in negative 4 into our first derivative, it's going to give us negative 64. At negative 1, we get positive 8. And at positive 1, we get positive 16. All right, so again, let's look at what this first derivative test is telling us about the slope, about the direction of our function. So before this first critical point at x equals negative 3, since the slope was negative, that means our function was decreasing. So it was coming downwards, it was decreasing, and then it zeroed out at negative 3, and then the slope of our function became positive, meaning our function started to increase or started to come back up, zeroed out again at the second critical point at 0. But notice here that at the second critical point, the slope still remained positive, meaning the slope, meaning the function continued to increase even after it zeroed out, even after the slope zeroed out. All right, so around that first critical point at x equals negative 3, The slope change from negative to positive. And when it changes from negative to positive, that indicates a relative minimum. So we have relative minimum at x equals -3. But notice in this case, since it remained positive, since the slope, so the function continued to increase after that certain critical point, since there's no sign and since there's no change in direction here, then that means at x equals 0, we have neither a max nor a min. Instead, we call it that known as there's no change in direction, we have what's known as a saddle point. So here we have a saddle point at x equals 0. So here we have found only one relative extrema, a relative minimum at x equals -3. Okay, there we went. All right, so we have relative extrema, or in this case, it's a relative minimum at x equals -3. And again, to find the actual value of that minimum point, plug in our critical value, plug in our critical number into the original function. So f at -3. So if we plug in -3 into the original equation, that should give us, let's see, -3 to the 4th plus 4 times -3 to the 3rd minus 15 should give us here -42. So the minimum can be located at -3, -42. All right. So now for the second part, the concavity. All right. So now for part B here. To determine the concavity is like determining the relative extreme of a function except using the second derivative. So now we have to find the second derivative, f double prime of x. So again, our first derivative was 4x cubed plus 12x squared. So taking the second derivative is going to give us, let's see, the derivative of x cubed will be 12x squared plus derivative of 12x squared will be 24x. So our second derivative is 12x squared plus 24x. All right, and once again, we set this equal to 0. I'm just going to rewrite this in a different form. It's going to take this second derivative, set equal to 0, because we want to solve for the zeros of this second derivative now. And just like we have done before, try to see if we can factor anything out before we start solving. 12 and 24 have a 12 in common. X squared and x have one factor of x in common. So let's take out a 12 and one factor of x, leaving us here with the inside of x plus 2 equal to 0. All right, set each factor of x equal to 0. So again, we're going to set 12x equal to 0, and also x plus 2 equal to 0 here. Let me write that. I'm just going to set 12x here on the outside equal to 0, as well as x plus 2. Okay, and then solving for x, we're going to get here 0 and -2. So we have found two possible inflection points. Or IP, inflection points. Now, to determine the concavity around these inflection points, we got to do the number line test. Again, it's not called the second derivative test. It's just referred to as the number line test. So, how we set this up is pretty similar to the first derivative test, except now we're testing the second derivative. So we draw once again, draw a number line, draw two inflection points, which were at -2 and 0. So -2 somewhere around here, 0 somewhere around here. And again, we want to determine the concavity of our function based on around the second derivative. Meaning we're going to take these test points that we pick and plug them in the second derivative. So if we plug in -2 and 0, we plug in these two inflection points that we found, if we plug them back into our second derivative, it's going to give us 0 each. Okay, because again, these two numbers were the zeros that we solved for from the second derivative. All right, so let's pick some test points here. Let's do, say, -3, -1, and 1. And again, we're plugging these in into the second derivative. All right. Yeah, where our second derivative was 12x squared plus 24x. So 12 times -3 squared plus 24 times -3. That should give us 36. And then plugging -1 into the second derivative should give us -12. And then plugging +1 into the second derivative, 12 times 1 squared plus 24 times 1 should give us 12 plus 24, which is 36. Okay, so before this first inflection point at -2, so the second derivative was positive, since it was greater than 0, then that means our function was concave up before hitting -2 along the x-axis. Again, if the second derivative is positive, that means your function is curving upwards. But then after -2, since the second derivative is negative, in that case, since the second derivative was less than 0, then that means after -2, our function started to concave down. It started to open downwards. Okay, but then after the second inflection point, since the second derivative becomes positive again, that means after 0, after our function hits 0 along the x-axis, it starts to open upwards. Okay, so look at what we have here. We have two intervals in which the function will be concave up, and then one interval in which our function is opening downwards. All right, so to determine the concavity of this function, our function seems to be concave down. Let's see here. Between -2 and 0, between our two inflection points, or its function is concave down between -2 to 0. And again, these are open intervals, not exclusive, not closed intervals, open intervals. Okay. And then our function was concave upwards at two separate intervals. It was concave up before -2 and then after 0. Again, this means that if we pick any number before -2, like -3, -10, -1,000,000, the second derivative will be positive. So our function is opening upwards from -infinity up to -2. So it's concave up from -infinity up to -2. But it's also concave up when x is greater than 0 up to positive infinity. So our function is concave up if x is less than -2 or if x is greater than 0, meaning our function is concave up from -infinity to -2, or when it's from 0 to positive infinity. All right, we're using the union symbol to combine these two sets. Okay, concave up from -infinity to -2, but also concave up from 0 to positive infinity. And since we have a change in direction here, and the concavity and the curvature of a function along these 2 points, then -2 and 0 are both true inflection points. So we have 2 inflection points here. Okay, one at x equals -2, and to find the coordinates of that inflection point, we plug in -2 into the original function. into our original function that we have above here. So we're plugging -2 into this equation here. So -2 to the 4th plus 4 times -2 cubed minus 15, which should give us, what would that be? -31. So the first inflection point is located at -2, -31. And then the second inflection point is at x equals 0. And if we plug 0 into the original function, that gives us -15. So our second inflection point, where the function changes its curvature, its concavity, can be located at 0, -15. All right. Again, when we have a change in concavity, here it went from positive to negative to positive. When there's a change in concavity, then those zeros that we found from the second derivative are inflection points. And again, let's visualize this here. Oops, let's visualize. All right, so here we have that old equation. Oops. All right, so here we have x to the 4th plus 4x cubed minus 15. Okay, let me set my windows here based on what we found. So I'll do from, there should be fine, I think, for that. All right, and then for the y values, since we have pretty small numbers, let's do -50 to say 10. Okay, so there we have that function. Wait, hold on. Oops. Yeah, we can write that correctly. Yeah, x to the 4th plus 4x. There we go. Why is it showing this first equation? There we go. All right. So again, here we see our relative minimum here at -3, -42. And before that hits that relative minimum, our function is coming down, it's decreasing. And notice when it's decreasing, it has an upwards type of shape, upwards parabola, so it's concave up around that area. So it's a concave up. And then somewhere around -2 here, it starts to come down a little bit, and the function zeroes out at this next critical number at 0, -15. But after that critical number, it continues to go upwards. And meaning our function is also opening upwards from there as well. Okay, so here's concave up, has slight concave down here from -1 to 0, and then, or from -1 to 1, I should say, really, from -1 to 1 before it starts to open back upwards. All right. Let's do one more example.